We begin this chapter with a discussion of graphing, and I suspect this is a topic you've had before, so we're going to hit the high points rather quickly. Graphing takes place on a platform called a rectangular coordinate system, sometimes also called the Cartesian plane in honor of the great French mathematician René Descartes. At any rate, the coordinate system is the intersection of two number lines. There's a horizontal number line called the x-axis, a vertical number line called the y-axis. The two number lines intersect at 0 on both number lines. That point is called the origin of the coordinate system. Now, notice that the intersection of the two number lines subdivides the entire plane into 4 regions. These are called quadrants, and they're numbered from the upper right quadrant counterclockwise. This is quadrant 1, quadrant 2, quadrant 3, quadrant 4. Points are located on the coordinate system using ordered pairs of numbers. Now, those ordered pairs of numbers are called coordinates, and they are coordinated because the first number is referred to as an x value and the second number a y value. I think a better way to look at these two numbers is that the first number is a horizontal distance and the second number is a vertical distance. We could say that we go along the x-axis with that number and the y-axis with this one, but horizontal and vertical distances, I think, serve us very well in this matter. At any rate, we locate points like this. These are the coordinates of a certain point, so to find the point associated with those coordinates, we come over here and we start at the origin, and we go a distance of 3 along the x-axis, or 3 horizontally. So from here, positive 3 is out this way 3, and then 5 is a vertical distance of 5, so 1, 2, 3, 4, 5. So here then is the point 3, 5. What we're doing here is plotting a point. We're plotting the point described by these coordinates. All right, the next point is negative 4, 2. We start at the origin, and if the first value is negative 4, we go in the negative direction 4 units, 1, 2, 3, 4, and then up 2, 1, 2. Here's the point then, negative 4, 2. The point negative 6, 0 means, let's see, the first coordinate, horizontal distance, negative 6, negative 6, 1, 2, 3, 4, 5, 6. And then 0 for the y component, or the vertical distance, means we go no distance up and down. So we're right here on the x-axis. So here's the point then, negative 6, 0. The point 3, negative 4, 3, positive, 1, 2, 3. Negative 4, that means down 4, 1, 2, 3, 4. So here's the point 3, negative 4. So we are plotting points. We are constructing the graphs then associated with those coordinates. Another task that we need to be able to perform is to describe the coordinates of any location on the coordinate plane. For example, this location. What are the coordinates associated with that point? Well, let's see, all we do is go from the origin and we count over horizontally first and then vertically, and we are describing the coordinates of the point. So from here, we would go over to 6 and then up 2, so the coordinates would be 6, 2. And for a point, let's say over here, from the origin, we would have to go negatively on the x-axis, a negative horizontal distance, so 1, 2, 3, 4, 5 in the negative direction. So negative 5 for the x component, or the first coordinate. And then, let's see, we go down 1, 2, 3, so negative 3 for the second component, second coordinate. Graphing takes place by using a method called the point plotting method. Now, we'll look at several methods of graphing, but the most basic is called the point plotting method, and it happens also to be the method used by graphing calculators. Now, the point plotting method involves finding the points to plot as a first order of business. So given an equation like this, we find the points to plot by making a table of values. Now, that table of values can be made like this. It can be made a couple of ways, but here's a most basic way. We set up a couple of columns here for x and y values. We want the equation, we would like the equation to be in a form like this, where one letter is isolated on one side of the equation and the other letter appears in an expression on the other side. That just makes it easy to evaluate the table of values. Now, in this one, it's pretty easy to pop in values of x and find subsequent values of y. And we do that like this. Suppose we let x take on an arbitrary value like, let's say 3. Now, if x is 3, we just imagine if we replace x with 3, we have 2 times 3, 6. 6 minus 3, that's 3. So when x is 3, y is also 3. What about when x is 5? Well, let's see. We imagine replacing x with 5. 2 times 5, 10. 10 minus 3, that's 7. You see, now, what we're really establishing here are solution points associated with this equation. You see, this xy pair will solve that equation. I mean, imagine if we replace y with 7, that becomes 7. If we replace x with 5, then we have 7 equals 2 times 5, 10, minus 3, 7. 7 equals 7, yes, that's true. So we are describing xy pairs that solve that equation. These are solution points of the equation. Important idea. Suppose x is 0. If x is 0, we have 2 times 0, 0. 0 minus 3, negative 3. So y is negative 3 when x is 0. How about, let's say, 1. 2 times 1, 2. 2 minus 3, negative 1. We have enough points to plot here. Let me pop in a couple more. How about negative 2? If x is negative 2, we have 2 times negative 2, negative 4. Negative 4 with negative 3, that's negative 7. Now let's plot the points. Okay, we have the point 3, 3. Over here on our coordinate plane, 3, 3. Go over 3, up 3. Boom, there's a point. Next point is 5, 7. Here's 3, 4, 5, up 1, 2, 3, 4, 5, 6, 7. Next point, 0, negative 3. 0 means no distance this way. Negative 3 is down 3. Then the point 1, negative 1. From here 1, then negative 1. The point negative 2, negative 7. Negative 2, negative 1, 2, 3, 4, 5, 6, 7. Notice that the points lie in a line. They are collinear. And the graph then of this linear equation is a relatively straight line. It should be a straight line. And that's an important aspect of graphing linear equations. We don't need a lot of points to describe a straight line. All we need really is 2. So if we put 3 points, 3 sets of coordinates into our table of values, we would be fairly safe if they turn out to be collinear. We know that we have points that are truly solution points. Now, I want to mention one of the great mysteries of mathematics to you, so get ready to be impressed. There's a tremendous relationship between graphs and equations. This is a very, very important point. Everything else was just build up to this very important point. The relationship between a graph and its equation is that the graph is truly a picture of the entire solution set for that equation. That is, if we take any point on this graph, like this point, and describe that point using coordinates, and let's do that. Let's see, the coordinates of this point would be 1, 2, 3, 4, then 1, 2, 3, 4, 5. So this is the point 4, 5. Now, the coordinates of that point, which is on the graph, will solve this equation. Now, x is 4, y is 5. So the y is 5, x is 4. 2 times 4, 8. 8 minus 3, 5. 5 equals 5. It solves the equation. And that's true for every point on this graph. All right, so this is truly a picture of the entire solution set for that equation. Very important idea mathematically. Now, to discover whether or not we have solution points, what we have done over here is we have replaced within the equation the values that we have at hand for x and y. Let's decide whether or not we have solution points for this equation. Are the coordinates 2, 10? Does this represent a solution point for that equation? Well, we can tell by putting the values into the equation. X is 2, y is 10. So I'll bring down this equation, and as I do, I'll replace x and y with these values. Okay, the y is 10. The x is 2. And I'll bring down the minus 7. So we have 10 equals, and I really should put a question mark here. I'm not sure they're equal until I actually evaluate over here. 10 times 2, 20. 20 minus 7, 13. No, 10 is not equal to 13, and so this is not a solution point. How about the point negative 2, negative 27? Well, if y is negative 27, I'll replace y with negative 27 and x with negative 2. And I evaluate on the right side. 10 times negative 2, negative 20. Negative 20 with negative 7, that's negative 27. We have a true statement, and therefore this is a solution point. So that's the whole idea here. On this one, on C, we have, let's see, 5 and 43. Y is 43, so I have 43 on the left side. On the right side, I have 10 times 5, then minus 7. So 43, I should put a question mark here. I didn't do that over here, but I should have. We have 10 times 5, 50. 50 minus 7, that's 43. 43 equals 43. Oh, happy day, this is a solution point. For this one, let's see, y is 5. And x is 1, so we have 10 times 1 minus 7. 5 then equals 10 minus 7. Oh, that's 3. No, 5 is not equal to 3, so that is not a solution point. In the introductory chapter, we talked about distance along a number line, and at that time we decided there were a couple of ways of calculating distance. Here's the number line. Suppose we want to calculate the distance between negative 2 and 3. We said one way we could do it was to take the larger number and subtract the smaller one. You see, and that's all there is to it. So it would be 3 minus negative 2, that's 3 plus 2, or 5. So the distance between negative 2 and 3 is 5 units. Of course, we could just count. We could say, okay, here's negative 2, here's 3, let's count. From here, 1, 2, 3, 4, 5. Very simple. When we bumped into absolute value, when we talked about absolute value, though, we said that, gee, it doesn't make any difference whether we use the larger of the two numbers first or not. That is, we could say that the distance between a couple of points is just the absolute value of their difference. So we could take the first one, subtract the second one, then we get the absolute value of negative 5, which turns out to be 5. And more generally, the distance between A and B is calculated as the absolute value of A minus B. All right, with that in mind, with that backdrop, we're going to establish a formula for finding the distance between any two points in the coordinate plane. That's our goal here. Now, the basis of the idea is this, that given this point and this point, we'd like to find the distance between them. We'd like to find the length of this segment. Now, suppose I extend a horizontal segment out this way and drop a vertical segment down here. With this horizontal and vertical segment idea, I have a right angle formed and a right triangle. Now, with right triangles, you know that the Pythagorean theorem allows us to establish a relationship between these sides. And that if this side is labeled C, and this one A, and this one B, then C squared is A squared plus B squared. C squared is A squared plus B squared. Now, let's talk about these distances. First of all, let me establish this point. This is the point, well, let's see, the horizontal distance here is 8, and the vertical distance 3. So that's the point 8, 3. Now, let's talk about C in terms of using the Pythagorean theorem. We know then that C squared is, well, let's see, A squared. A is a distance. It's a horizontal distance. It's a distance along a real number line. We could think of it like that, and therefore we could think of making the calculation as the absolute value of the difference in horizontal components, that is, the difference in between 2 and 8. So we would have the absolute value of 2 minus 8 for this distance. All right, let's go up here and do that. So we'd have 2 minus 8, and that amount would be squared. Then plus, and similar idea for the B distance. This B distance is a vertical distance, and all we're doing is taking the difference between the y components here. So it's the absolute value of 11 minus 3 or 3 minus 11. Doesn't matter which way we write them because of that absolute value idea. Okay, so it's the absolute value of, and I'll write it as 11 minus 3. Now, recall that the absolute value was put into that kind of problem, this distance problem, to assure ourselves that we have a positive value that we're dealing with. Well, in this environment, whether the number here is positive or negative, if I take out the absolute value symbol, when I square a positive or negative number, I'm going to get a positive result. So really, the absolute value symbols are not necessary. So I could say then that c squared is 2 minus 8 squared plus 11 minus 3 squared. Now, notice that I'm not evaluating anything here. I'm going to generalize the situation here in just a second. I just want to kind of develop this as a formula. And it turns out that C, the hypotenuse of a right triangle, is indigenous to right triangles. And really, we just want a distance from one point to another. So instead of writing this as C, I'm going to write it as D, distance between the 2 points. So I'll replace this C with a D, the distance between the 2 points. All right, that's the idea. Now, if D squared is this amount, then D, it turns out, is the square root of that amount. Okay. Now notice something else, that in order to find A, I took it was the absolute value of the difference between the 2 and the 8. Now this 8 and that 8 are the same, so I really don't need this 8. I can just look at that 8. After all, I'm talking about horizontal distance associated with these 2 points. And if I think just horizontally, just think like this. See, the horizontal distance to this point is 2. The horizontal distance all the way over here is 8. And I want the difference between those two. So I really don't need that point at all, you see, for that purpose. And in a similar way, for the B value, for this 3 happens to be contained right here. So when I think about vertical distance, you see, I can just look at the y components of the 2 given points. So I really don't need that point at all. All right, that's the idea. And generally then, I only need the xy pair here and the xy pair here. So I can generalize this idea into a formula like this. I can say this is the square root of, now remember, this was the difference in x components. So I can say it's one x value minus the other. And I can use subscript numbers to designate a difference in x values. I'll call the first one x subscript 2 and the second one x subscript 1 for no real reason other than the fact that this is the way it's written in your textbook. I could write this as x subscript 1 minus x subscript 2. The 1 and the 2 are just here to designate these as different x values. Okay, and then plus, and then these are the different y values, so I'll designate them as y subscript 2 minus y subscript 1. All right, so here then is our distance formula. Now we can use it to find the distance between the 2 points that were given. And remember, we don't need this right triangle. All we need, see, we don't need any of this business, really. All we need to use the formula would be the coordinates of the 2 points that are given. So if we were calculating the distance between these 2 points, we would use our distance formula, we would plug into it, and we end up plugging in the values that we see here. And let's go ahead and evaluate it down here. So we're actually we would be going from here to there and then back down to here. So the distance then is the square root of, well, let's see, and look at this, 2 minus 8, that's negative 6. Negative 6 squared is 36. And then 11 minus 3 is 8. 8 squared is 64. Let's see, we have distance then is the square root of 36 and 64. Oh, that's 100. The square root of 100 is 10. So the distance between those 2 points is 10. Let's take it from the top. That is, given 2 points, let's find the distance between them. Let's find the distance between the points negative 1, 2 and 2, 4. You always start a problem associated with a formula by writing down the formula. So I've written the formula down. Now, don't make the mistake of trying to short-circuit the situation and skip a step by plugging into the equation as you write it down. Don't do that. You'll end up making some careless mistakes as the situation becomes more and more complicated. So just to establish a habit of writing down the formula, and in the next step, replace letters with numbers. Don't try to figure anything out. Don't try to evaluate anything or perform any operations. Just replace letters with numbers. That's all. So we would have the square root of, let's see, we have a difference in x components. Now, it doesn't make any difference whether this is x1, y1, or that's x1, y1. Really makes no difference at all. So we could just write -1 minus 2. So it's just a difference in x components. So one x component minus the other x component. That's all we have to think about. And then this is a difference in y components. So this is 2 minus 4 squared. And now we go through the process of evaluation. Let's see, -1 with -2 is -3, but -3 squared is 9. And here, 2 minus 4 is -2. -2 squared is 4. 9 and 4, 13. So the distance then is the square root of 13. We can't take this evenly, so presumably we would use our calculator to make an approximation, and it turns out to be approximately 3.61. Now, a very interesting aspect of the Pythagorean relationship is this. You know, the relationship says, usually we use it like this, that given a right triangle, c squared equals a squared plus b squared. That is, the square of the hypotenuse is equal to the sum of the squares of the legs. You see, we usually start with the idea that we have a right triangle. But it also turns out that if we have any old, ordinary, everyday household triangle, and it turns out that that special relationship exists among the sides, that is, the square of the long side is equal to the sum of the squares of the other two sides, then we can conclude that we have a right triangle. You see, so we have this if-then idea going in both directions. If we have a right triangle, we have a relationship. But if we have any triangle and we have the relationship, we have a right triangle. That's the idea. So it's kind of we call that an if and only if situation mathematically. Suppose we use the idea sort of backwards in the right, with the right triangle and the Pythagorean theorem and answer this question. We want to show that the points 1, 2, 3, 1, and 4, 3 are vertices of a right triangle. We want to show that we have a right triangle. And to do that, we show that this relationship between the sides exists. Now, I've plotted the 3 points, and these are the 3 points. And if we think about connecting them, you see, it's hard to tell, but because of the justification of those vertices, whether or not we have a right triangle. Now, if we do, then it kind of looks like this would be the right angle. But we're not sure that it is. Okay, let's find out whether it is or not. Now we know, here's our distance formula. If we call this D, let's call it D3, and call this D1 and D2. You see, here's what we're trying to show. We're trying to show that given a triangle, if it is true that the square of this distance plus the square of that distance is equal to the square of this distance, then we do have a right triangle. So we're saying, is it true that D sub 3 squared is equal to D sub 1 squared plus D sub 2 squared? Is that true? Well, we only know by calculating these 3 distances and then putting that information into this model. Okay, let's do that. D sub 1. Now, I'm using the distance formula. So I would have, let's see, for D sub 1, I'm looking at the coordinates of these 2 points. So I want a difference in x components squared, so that's 1 minus 3. So I have 1 minus 3 squared. And then a difference in y components, that's 2 minus 1 squared. It's hard to resist the temptation to make the calculations as I go, isn't it? But notice that I'm doing that. I'd like you to do that too. Okay, and then let's see, we make the calculation as, now I'm going to do a lot of calculating at this point because I don't have a lot of room down here, but 1 minus 3, -2. -2 squared is 4. So we have 4 here, and then 2 minus 1 is 1. 1 squared is 1. So 4 plus 1, 5. This then is the square root of 5. Okay, for D sub 2. Now I'm plugging into this relationship, and for D sub 2 I'm looking at the coordinates of these 2 points. So I've got, let's see, the square root of difference in x components. I have 4 minus 3. So 4 minus 3 squared plus difference in y components, 3 minus 1. So 3 minus 1 squared. And now what is this? This is the square root of, well, let's see, 4 minus 3, that's 1. 1 squared, that's 1. 3 minus 1 is 2. 2 squared is 4. So 1 plus 4, 5 under the radical. So the square root of 5. Now, for what about d sub 3? I've got square root of, see, d sub 3. These two. 4 minus 1 squared. Difference in y's. 3 minus 2 squared. Okay, what is this? We have 4 minus 1, that's 3. 3 squared is 9. 9 for this business. 3 minus 2, 1. 1 squared is 1. 9 plus 1, that's 10. So we have here the square root of 10. All right. So d sub 1, square root of 5. D sub 2, square root of 5. D sub 3, square root of 10. Let's see. In this model, d sub 3 was the square root of 10. It's squared. D sub 1, square root of 5, squared. D sub 2, square root of 5, squared. Squaring a square root gives us the number under the radical. We'll study more about that in a little bit, but in another chapter. But for now, we'll just assume that that's true. And you've probably had that before, I'm sure. Squaring the square root of 5, we get 5. Squaring the square root of 5, we get 5. 10 then is equal to 5 plus 5 equals 10. So this relationship is true, and therefore this is indeed a right triangle. If we know the coordinates of 2 points on the coordinate plane, we know that we can use the distance formula to calculate the distance between the 2 points. Well, there's also a formula for finding the midpoint between those 2 points, and it's rather intuitive. That is, the method of calculation is rather intuitive. It works like this. Suppose we have a couple of points on the coordinate plane. We'd like to find the coordinates of the point that's right in the middle between those two. The midpoint formula conceptually works like this. It's just the average horizontal distance. You see the average of the horizontal distances associated with the coordinates of those points and the average vertical distance for the y component of that midpoint. So it's average horizontal distance, average vertical distance. And averages, you know, are calculated by taking some number of things and adding them and then divide by the number of items that you have added. Now here we're just averaging a couple of horizontal distances and a couple of vertical distances. So we're adding 2 x values and we're dividing by 2 to get the average. And then you add a couple of y values and divide by 2 to get the average. And that's really all there is to it. So it's add the x components, divide by 2, add the y components, divide by 2, and these are the coordinates then of the midpoint. For the points that we have here, the x components are -3 and 7. Collecting those and dividing by 2, we get 2 for the x coordinate of the midpoint. The y components are 1 and 5. Adding those and dividing by 2, we get 3 for the y coordinate of the midpoint. The midpoint then has coordinates 2, 3. Let's see, 2 and up 3. Aha! Here's the midpoint of this segment.